I want to devote the last lecture to finally a proof using sheaf-theoretic methods of Poincare duality for intersection homology groups. So in the last lecture, I gave a very fast introduction to sheaf theory, and we will deploy this technology today to prove Poincare duality. And then, as time permits, the plan is to talk a little bit about width spaces and their signature and its properties. Okay, so let us first talk about the intersection chain sheaf. More precisely, it will be a complex of sheaves, but I will sometimes just simply say sheaf, even though I mean a complex of sheaves. So we start with a pseudomanifold. Let Xn be and first it will be a PL stratified pseudomanifold, although later it will be a topologically stratified one, and this will be sufficient. But for now, let Xn be a PL stratified oriented pseudomanifold. For such pseudomanifolds, we've defined intersection chains over open subsets. So let's say U is an open subset in X. For every open subset, we have intersection chains. We fix a perversity P. But the important thing to remember is that we worked with infinite chains, with Borel-Moore chains. Right? So this becomes now, as I already alluded to earlier in this week, becomes very important at this point now. Because since we use infinite chains, there is a restriction map from IC U to IC V if V is an open subset in U. And this would not be possible had I used finite chains earlier, right? So I have this, and this allows me to define a presheaf on X, which assigns to an open set this group. So this is a presheaf on X. Now the next thing you observe is that this presheaf actually satisfies the gluing condition and therefore is already a sheaf. So it satisfies condition G that I formulated yesterday, and thus is a sheaf, more precisely again a complex of sheaves, which I'll denote IC. So if we fix the degree I, then it is a single sheaf, but I want it to be indexed by negative I, and the reason is the boundary map in this chain complex lowers the degree by 1, but we discussed the formalism of differential complexes of sheaves where the differential goes up. But I can achieve this by a simple trick by indexing. Of course, it doesn't really matter, right? So I index with the negatives of the degrees, and then it will go up. So that's a simple trick. So this is important. This gets changed here. Sometimes it's associated to X, although sometimes I will omit this. So we get a sheaf, and the next fact that one can observe about this is that it is a soft sheaf. So this complex of sheaves is, so this is a complex of soft sheaves. Of course, this requires proof, but we'll skip this here. But once you know this, it has the following consequence. The hypercohomology in degree I with coefficients in this complex can be computed without first forming an injective resolution. I can use this complex directly, and we discussed this yesterday, right? So because of this, because of the softness, this is simply, so I can take sections, global sections of that very same sheaf, and then simply take the cohomology of that complex. But furthermore, since the condition G is satisfied, I can compute those sections by the defining pre-sheaf groups. And those are these groups, and the cohomology of these groups is just intersection homology in the PL sense, as we defined it in the beginning of the week. So this is just IH negative I P of X. And so you see then that we may think of intersection homology, as we defined it in the beginning of the week, also as the hypercohomology of this complex of sheaves, right? So let us investigate further the properties of that complex of sheaves. So what I'm particularly interested in is the stalks. What are the cohomology stalks? Of that complex. So suppose X is a point, and I want to know what is HI, and remember this is the cohomology sheaf of the complex in degree I. What is the cohomology sheaf and its stalk at X of ICP? So, which by the way could also be written, of course, as Jx star, where Jx is the inclusion of the point into X. Then I can write it, if I want to write it very functorially, I would say I apply that restriction functor to this complex and then compute the cohomology of that over a point. But from yesterday, from the crash course on sheaf theory, we remember that such cohomology stalks can be calculated as the hypercohomology of a sufficiently small distinguished neighborhood of that point. Right? So here, Ux is a small distinguished neighborhood. But what does distinguished mean? That means that Ux is isomorphic to, well, suppose X lies in a stratum xn minus k minus xn minus k minus 1, in a pure stratum like this. Then the distinguished neighborhood takes the form Rn minus k cross open cone on the link, which is then k minus 1 dimensional. So we have to compute this. But from what we just observed here, this is just an intersection homology group. So this is furthermore equal to IH, but then I mustn't forget to turn the sign around of R n minus k cross cone on L So we have to compute this. But we did this earlier in the week, right? Because there were two steps. One step was we can remove the factor of Rn to r to the n minus k one at a time by using the suspension isomorphism, right? So that was one of the things we discussed. In Borel-Moore homology, we have the suspension isomorphism. So therefore, this is isomorphic to, and this is the suspension isomorphism in Borel-Moore homology. So minus I minus n plus k, and then what remains is the cone on L. And so everything, as we said earlier, this all boils down ultimately to what happens on the cone, but there we made a detailed calculation of what happens for the cone, and we saw that this is the intersection homology of the link itself. Now the degree is minus I minus n plus k minus 1 of L and 0. And this was, if you go back in your notes and look at the calculation that we obtained for the cone for the Borel-Moore chain picture, then this will be 0 when I is greater than pk minus n. And you get this when I is less than or equal pk minus n. And so now we have a complete understanding of the stalks of that sheaf complex. So I will actually call this axiom 2. So axiom 2, suppose now we have some object of the derived category on X. Then let's just take this kind of behavior as an axiom that is clearly suggested by this. So I just say the same things, Hi, and now for any sheaf complex A, Jx star of A should be 0 when I is greater than pk minus n. Of course, when X lies, so under this condition, where X is a point in the stratum xn minus k minus xn minus k minus 1. So I call this condition on a sheaf complex A, I call it axiom 2, because there will also be an axiom 0 and an axiom 1, but I'll do that in a second. So I call it axiom 2. And so dually, I can do this for the Schrieg restriction, and I will see that so if instead of looking at Jx star, I look at Jx Schrieg, then this is 0 for I less than or equal pk minus k plus 1. Now you make a similar calculation because we said also yesterday that this can be computed as the hypercohomology again of a sufficiently small distinguished neighborhood, but with compact supports. The difference is you have to look at compact supports. And then you have to compute that group with compact supports, and it will exactly lead you to this vanishing. In other words, looking at the group with compact supports is like looking at our intersection chains with finite support, with finite intersection chains. And if you look at the result we had on the cone for IH finite, and you also take into account that you have to turn the sign of the I around, then you get exactly what's written here. Right? So that's how you show that. Okay, and so now I take this as the basis of another axiom. I say, let's call AX3 the condition on a sheaf A that HI of JX shriek should vanish in degrees I less than or equal pk minus k plus 1. Of course, I won't write it down again, but where x is in that stratum. Now, as I say, one can observe two more properties that the intersection chain sheaf happens to have. One thing is what happens over the top stratum, or what would it look like if the entire space were in fact not singular, but were in fact a manifold. Right? So that's another good question. So what happens if I take that sheaf and restrict it to the top stratum, that is X minus the singular set? Well, of course, then there is no difference between the sheaf. So here C is the sheaf of all PL chains. Of course, Borel-Moore, right? I can, of course, place no restriction at all, or in other words, take the perversity very high so that there's no restriction. Then I get all PL chains, and if I restrict this, then right near any point here, there is no difference. Right? So these are isomorphic. Remember, from now on, all isomorphisms, by the way, will be in the derived category. I won't say it anymore, but it's now understood that we are always working in the derived category, of course. So in the derived category, then, this is the same, or isomorphic to, well, in general, the orientation sheaf on X minus sigma, but there is a shift by n due to our indexing conventions. So again, this is in the derived category. And then further, since we assumed, so as X is oriented, this, however, is furthermore comes with a trivialization, that is to say an isomorphism to the constant sheaf R. Aha, so we take that as the basis of another axiom. So we formulate an axiom 0 for a sheaf A restricted to the top stratum should be isomorphic to the real sheaf on X minus sigma shifted by n. This is sometimes called a normalization axiom. And also we can observe, and this I'll call axiom 1, that there are no cohomology stalks below negative n. Remember, I defined yesterday what the shift is. So it means that that sheaf actually sits in degree negative n, right? According to how I defined the shift. So another axiom is that the cohomology of A is 0 when I is less than negative n. And this is true for IC. This is clearly true for IC. So we are led by these considerations to an axiomatic system, to an axiomatics AX0 through AX3 in the derived category of bounded constructible sheaf complexes on X. All right. So let me next discuss Delin's sheaf. So I'll use the following notation. So some notation. UK will be the complement of xn minus k, this closed stratum, the complement of the closed stratum of codimension k, that I'll call UK. IK will be the inclusion of, so this is an open subset in X, right? So I get all these open subsets UK. And UK is included into UK plus 1, where you adjoin the next stratum to UK. So this is an open inclusion. And then I'll call JK the closed inclusion of the rest. So of UK plus 1 minus UK into UK plus 1. So this will be my notation now. So the question is, can you build a sheaf that satisfies all of this, all of these axioms, functorially, just by applying the standard functors of sheaf theory that I've described yesterday, rather than saying all these PL conditions on transversality and deviation from transversality for chains, right? And you can. And the answer is as follows. Well, there is not really much choice as to how you can start to begin your sheaf, because you better start like this if you want this to be satisfied, right? So we better start with R on X minus sigma. And so now here's what you do. You push this forward under I2. Remember that, so this is the same as U2, right? And now you push it forward under the inclusion to the next stratum. But of course, we must take the derived functor to be entirely precise, right? But then these Stock vanishing conditions need not hold, right? This need not hold necessarily, because you have to replace the complex by an injective resolution and push that forward when you compute the derived functor. But then you may have lots of stalks in principle again, essentially depending on how complicated the cohomology of the link is at each stage. And so therefore, to achieve this, we say we just truncate it. We want this, so we achieve it by brute force simply by applying our truncation functor. Right? So I say I apply tau. This is my functor tau from yesterday, less than or equal. Well, and what I have to do is, of course, I just have to take that value. Right? So I say I must truncate in pk minus n. And the case 2. And then I simply continue like this. This is now sort of an inductive process where at each point you continue like that. So I would now say take Ri3 star, truncate less than or equal P3 minus n, and so forth until you reach Rin star and tau P n minus n, and now you are at points, right? You are at x0 now. And so by now, this is a sheaf on all of x, right? This is a sheaf over U2, this over U3, this over U3, this over U4, over U4, etc. And so this is a sheaf on x, and we call it S. So I call it S. And this was Deleuze's suggestion. So Deleuze learned about these kind of Stock vanishing conditions that were observed by Goreski and McPherson, and he suggested, well, what you should really look at is this sheaf, because that's probably the same as what you have constructed with PL chains, and indeed it is, and I will prove that now. So notice here that by construction, yeah, and I will also, with this axiomatics, I will also say, I will abbreviate this and say a sheaf A satisfies AX. But sometimes I will also, we have to remember that this depends really on a choice of perversity. So sometimes I'll denote it like this, that we have to remind, especially when we discuss Poincare duality, we must be clear about for which perversity we consider the axioms. Okay, by construction, S satisfies this axiomatics for perversity P. I mean, we made it so, right? Well, there's perhaps something to show here, but I will skip this. Yeah, for the co-stalk, this is called the co-stalk vanishing condition. This is called, obviously, the stalk vanishing condition, and this is sometimes called the co-stalk vanishing condition. So we have at least two sheaves now constructed that satisfy the axiomatics. In the PL picture, we've constructed the IC sheaf. And we can also notice here that this sheaf is much more generally defined. This doesn't really require the PL structure at all. This would be perfectly fine if we just started with a topologically stratified pseudomanifold. And that's a great advantage, right? So we note S is defined on any topological stratified pseudomanifold. Whereas this construction isn't. So I want to prove the following theorem. If an object in the derived category satisfies the axiomatics for perversity P, then it is isomorphic to S, to Deligne's sheaf. Okay, so let's try to prove this. And this will then say, of course, immediately that the axiomatization AX determines a sheaf uniquely in the derived category. Because if you also have a B that satisfies it, then they are both isomorphic to S. So in particular, they are isomorphic to each other. So in fact, up to isomorphism, there's only a single sheaf that satisfies the axiomatics. So in the derived category, they are all the same. Although the actual incarnation may be quite different, which we have already seen here, right? But that's precisely the advantage of this axiomatics. Okay, so let's try to prove this. What I will need is I need a junction morphisms. So I believe those I haven't described yet in my review of sheaf theory. So let's do it here. So in general, if you have a continuous map between topological spaces from X to Y, and you have a, say, you have a sheaf on, you have a, say, a single sheaf on Y, then you can pull it back under that map to X and then push forward again. And you want to relate this to what you started with. Of course, you will not get the same thing in general, but I claim that there is always a canonical map going this way, and it will be called the adjunction map, because it actually expresses the fact that phi lower star and phi upper star are adjoint functors. But I just need this morphism. So, so explicitly, it can be described as follows. So let me describe it on sections. So if U is an open subset in Y, so then I need to describe this, I need to make a map. And the push forward, remember, was given by taking the pre-image under phi of an open set U, and then I have to take sections in the sheaf phi upper star B. Now, if I have a section here, what do I send it to? The adjunction map sends it to, now I have to specify a section of that sheaf over this set. So if I have a point X in this pre-image, then I can apply phi to it. But since phi of x then lies in U, certainly the section is defined on phi x, so I can take this, and this is the map. So this is called the adjunction map, and so we make use of that. Now, the whole proof is an induction on codimension K, on the codimension K. So the induction start is given by looking over U2. So for K equal 2, you look at U2 and you restrict. So we have these two sheaves, right? A. So there's your A, and you restrict it to U2. But then it's pretty clear that the statement is correct over U2 by the normalization axiom. By axiom 0, this is isomorphic to R over U2 with a shift by N. But the same is clearly true for S, right? By construction. And so if you compose these, they are at least isomorphic over U2. And that is the induction start. Now assume inductively that an isomorphism has been constructed over UK. And we wish to extend it to UK plus 1. So we extend the isomorphism to UK plus 1 as follows. So I consider the restriction of A to UK plus 1 now. And I look at the adjunction morphism for IK. So here is A, restricted to UK plus 1. So I apply IK upper star, IK lower star, and then there is an adjunction morphism going from here to here. And to that morphism, I can apply the truncation, because truncation is functorial. So I get a morphism from tau less than or equal p k minus n to tau less than or equal pk minus n of that pullback push forward. The pullback, of course, is just restriction, right? This term here is nothing else but A restricted to UK, of course, because IK is just an inclusion. So this morphism is tau of the adjunction that I described before. But this sheaf here is nothing else but a UK plus 1. Nothing happens actually when I truncate because that's one of my axioms, right? It is 0 anyway above pk minus n. So if it's already 0 to begin with, if I apply truncation, then nothing at all happens. So I have an isomorphism here. I go this way, and now I observe this is just A restricted to UK. But by our induction hypothesis, A on UK is already isomorphic to SUK. And that isomorphism, when I apply these functors to it, will still, of course, be an isomorphism. And so I see that this is isomorphic to tau less than or equal pk minus n, Rik star applied to S over UK. But this is just, but the entire sheaf, the entire construction of S consists of steps like that. So of course, what you get by definition, the definition says that this is S over UK plus 1. So I get a map. I get at least a map over UK plus 1 from A to S. And now what remains to be done is we have to argue that this is an isomorphism. So why is this? I claim that this is an isomorphism. Well, it's an isomorphism over UK. That's trivial. So we don't have to discuss this because there it's just given by this, and we know that this is an isomorphism. So it really remains to check this over UK plus 1 minus UK. And here now the idea is to bring in the Costock vanishing axiom. So far we haven't made use of the Costock vanishing axiom, but here it will enter now. And we bring it in as follows. We use the exact triangle. So I'll explain in a second. So there's the following structure. So remember in my notation, JK was this inclusion of the closed part of the new stratum that comes into the game into UK plus 1. So there are canonical maps from JK shriek to JK star, and then from there to JK star of IK upper star, R IK lower star. And then this continues raising the degree. So it will go to JK shriek shifted by 1 and continues like this. So why do we have to do this? What is this triangle? Let me say a word about this. The problem is the following. We noted that the category of sheaves is an abelian category, so it makes perfect sense to talk about exact sequences. Unfortunately, the derived category is not an abelian category, so there's no reasonable way of talking about exact sequences. But there is a substitute for that. The situation is not as terrible as it sounds. There is a very good substitute for exact sequences. They are called exact triangles. And so for all practical purposes, treat this like an exact sequence, okay? It isn't, but treat it as if it were one. In other words, to make this more precise, for example, if you took cohomology sheaves in this triangle, then of course you are in an abelian category, right? And then it becomes an actual exact sequence of sheaves. if you go to cohomology sheaves and so on. So it's, for all practical purposes, it's as good as an exact sequence. Okay, the derived category is what's called a triangulated category, but I cannot explain this here further, obviously. But you use that to relate this adjunction map to the Schrieg functor. That's the point, right? Because we know something about the Schrieg functor by the Kostock vanishing axiom. But if we know that this vanishes in a certain range of degrees, which is what is being asserted by axiom 3, then this will tell me that this map induces a cohomology isomorphism in a certain range of degrees, right? And the range of degrees is exactly this one. So, so if I apply these ideas, I can say the following. So to this map, I apply now jk upper star, because that's the restriction of the sheaf to that region. So I say jk upper star of tau less or equal pk minus n of A jk upper star. I mean, these are already isomorphisms. So of course I only have to show that jk star of this is an isomorphism here, right? So I look at that map in the middle here, pk minus n, and then rik star of A restricted to uk plus 1. So this argument, so now use, as I said, the point is to look at axiom 3, which tells me that this vanishes in a certain range of degrees, the Schrieg restriction, therefore this is an isomorphism, therefore this is an isomorphism, and the range where this happens, if you do the calculation, is exactly in degrees less than or equal pk minus n, so that when I restrict with jk star this map, it's also an isomorphism. So it's an isomorphism over this and over this, so it's an isomorphism everywhere. And we conclude that A restricted, so we have constructed an isomorphism from A on uk plus 1 to S on uk plus 1. And so, of course, by the induction, we then see once we've reached, once we've exhausted all of x with this, we will be then able to conclude that A is isomorphic to S, and that proves the theorem. All right, so this has several consequences, of course. Well, it has a lot of consequences. It's a key theorem in this game. It's a key theorem. We now know. So the axiomatics, the theorem shows that the axiomatics AX characterizes a sheaf complex up to isomorphism in the derived category. So if we're talking about complexes, then we could say up to quasi-isomorphism. Notice that this argument would be much longer had we not worked in the derived category. I mean, we're speaking of isomorphisms here, but some of these maps are actually maps that go into the wrong direction. They're only quasi-isomorphisms, so they become isomorphisms in the derived category. So I have, right? But without saying all of this, without the derived category, which would actually be rather complicated and take a long time, and the proof becomes only so simple because of the derived category. That's really something one should think about, right? So you can try to write this out, avoiding the derived category. So You can try to do it. Okay. So up to quasi-isomorphism, we have this characterization. Of course, if X is PL, then this also shows us, in particular, that the hypercohomology in degree I on X with coefficients in Delén's sheaf is isomorphic to the intersection homology defined with PL chains, as we did it in the beginning, negative I P X. And so this shows that Délén was perfectly right, that all of this geometric construction can just be described by this very elegant functorial formula in the sheaf language. Right? We can, and also this allows us, of course, now to even introduce intersection homology for topological pseudomanifolds, because we just define it like this, right? On a topological pseudomanifold, now define intersection homology to be the hypercohomology of this sheaf S. And we take it as our definition. It's perfectly justified. This is the right thing to do. And further, I want to apply all of this now in proving Poincaré duality. So the next theorem is, these are all theorems, by the way, of Goreski and McPherson, of course. I forgot to write it down here. These are, of course, due to Goreski and McPherson. And so is this. The claim is the following. I take IC, the IC sheaf for perversity P. I dualize it. Remember, we discussed the Verdier dualizing functor. And I have a shift. Then this is isomorphic to ICQ. So this is what I want to claim next. So let's prove this. Well, the Verdier duality functor D interchanges so this is, of course, where P and Q are complementary. That's, of course, important. The relation between P and Q is that, of course. So D interchanges the axiomatics, well, more precisely, the axiom 2 for P and axiom 3 for Q. That's the basic observation. That's what you have to check. So a little calculation checks, verifies that when you apply D, or maybe more precisely D with the shift, that will interchange that axiom with this one. And therefore also, and so it also exchanges, of course, AX3, because this is symmetric, it also interchanges AX3P and AX2Q. And thus, we may argue as follows. As ICP satisfies the axiomatics with respect to P, as we have shown, the dual of it therefore, by this remark, satisfies the axiomatics for Q. But so does ICQ, right? But so does ICQ. And therefore, by the first theorem that we proved today, which says that the axiomatics characterizes a sheaf complex uniquely up to isomorphism in the derived category, it is therefore true that the dual of ICP must be in the derived category, again that's very important, isomorphic to ICQ. And that proves the theorem. So the proof is extremely simple based on that very important theorem that we proved first. So this axiomatic characterization is kind of a key thing to observe. So now we actually already have Poincare duality in a sense. We have in fact a very powerful version of Poincare duality, namely not just a global one, but remember that the dualizing functor dualizes complex on all open subsets. So you can view this as an extremely powerful statement saying that you have Poincare duality not just for X, but over every open subset, right? So it's extremely powerful. It's much more powerful than just saying I have global Poincare duality. And now, of course, it's a simple corollary of this that you also have global Poincare duality. So I say corollary to that theorem, global Poincare duality. So in other words, there is a non-degenerate pairing between IHIP of X and IHN minus IQ of X to R. Everything here with R coefficients. Integrally, it need not, I'm not making an integral statement. Well, let's see. So IHI PX. So let's make this calculation. Well, it's H negative I on X hypercohomology with coefficients in the sheaf complex ICP dot. But by the last theorem about the Verdier dual, I can replace ICP with the dual of ICQ shifted by N. So I take the shift out. So it's the hypercohomology in degree n minus I of X with coefficients in the dual of ICQ. And now I apply properties of the dualizing functor. Here, of course, let X be a compact oriented topological pseudomanifold. So it works, of course, just topologically. I don't need any PL structure now. But let's say I want compact. Otherwise, I'd have to say something else here. Let's say compact. So then we know that this is equal to So how do I compute the dualizing functor? I have to say HOM and then H, but remember this gets turned around. When you apply the dualizing functor, you must write I minus n, and you must also write compact supports, but I can immediately delete it because I assumed now that the space is compact, but I'll just leave it for now. With coefficients in IC Q, R. But as I said, this I might actually cross off, and then I just have HOM. And now the group that I have here is just IH. And now I must turn around the sign once more, and it's n minus I of x, but with perversity Q, R. And now I have it. Right? So it follows very easily from the defining properties of the dualizing functor, and in fact the much stronger statement to make is this. Okay, very good. So now that we have Poincare duality, this has quite a number of consequences, because on Monday I started my lecture by saying that one important application of Poincare duality is the signature. So perhaps we should return to this now and think about whether we can use these ideas now to define a signature even for singular spaces. So let me speak about the signature for width spaces. Now I work with Q coefficients. Well, we might see, the problem is this. Why can we not immediately introduce a signature? Because the duality, this is because the duality holds, I mean, suppose the space X has dimension divisible by 4. That's the interesting case for the signature. Then we could go to the middle dimension, and then we could have, if n is 4k, I could put here 2k and then also 2k here. But what do I put here and what do I put here? That's a problem. So you say, well, you also go to the middle with that. You look at everything in the middle, and then you hope to get a quadratic form on just one vector space whose signature you could then take. So you say you take the middle perversity here. But the problem is there are two different middle perversities, a lower one and an upper one. So which one do you put? So you say, well, I choose one. Say the lower one. So you put the lower one here, but then you must put the upper one over there. And it's not always the same. They're not that far away from each other, but they're definitely, these groups are in general different, so you don't get a quadratic form whose signature you can take. So that's the problem, why you can't immediately say the same things that you said for manifolds. Okay, but this necessitates the following definition. So we just define a class of spaces where these two sheaves for lower and middle perversity are the same, and we just do it for those. Right? So it's right, so we just say definition Xn a PL pseudomanifold is called a width space, and this terminology and the investigation of width space is due to Paul Siegel. It's called so he termed these width spaces if the canonical map from the lower middle perversity to the upper middle one is an isomorphism in the derived category. So notice that if you have a smaller perversity and a bigger one, there is always a canonical map between them. For example, you can see this from Deline's formula very easily, right? If you use a Q here such that P is less than or equal Q, then clearly there's a kind of an inclusion map of complexes from this to the same formula for Q. Right? So that's the morphism I'm talking about here. And if this is an isomorphism in the derived category, in other words, if this is a quasi-isomorphism, then I call the space a width space. So now this is fairly abstract. If you're not used to working with these kinds of sheaves, then this is, looks not very geometric, right? So of course you would like to have a more geometric description of what this actually means about the geometry of a space. But this is equivalent to, equivalently, I could say it's a width space. You see, the problem is only, obviously, at strata of odd codimension. Because if the space only had strata of even codimension, then only the values of m and n at even codimensions would come in, but there they are always equal, and then this clearly would be an isomorphism, and so all these spaces are clearly width spaces. So we can note that immediately. So the problem arises only at the other strata, at strata of odd codimension. But these strata have links that are then even dimensional, so you can look at their middle dimension, right? So I must look at links of even dimension, let's say 2L, and I must look at their intersection homology in the middle dimension with the lower middle perversity, and I say these should vanish. Or so the middle intersection homology for all even dimensional links should be 0. Well, I hesitate to give this as a problem for the problem session. I originally thought I would give this as a problem, right? Show this equivalence. But I'm not entirely sure whether it's suitable. I mean, we can say a few words about it later in the problem session. If you like, you could think about it, why this is actually so. All right. So let's do some examples. The suspension of CP3. Is that a width space or is it not? What do you think? So you must know what is the middle homology of CP3. So the real dimension is 6, so the middle dimension is 3, so what is H3 of CP3? Is 0, right? And so therefore it is a width space. So this is width as H3 of CP3 vanishes. On the other hand, if we took the suspension of, say, a 2 torus or a suspension of CP2, for instance, then these are not width, because, for example, here the first homology of T2 does not vanish, it has rank 2, so it's not a width space here. The middle homology has rank 1. So H2 of CP2 has rank 1, so this is also not a width space. So, so these are some examples. But perhaps the most important class, as I mentioned, there's a very large and extremely interesting class, of course, of width spaces, which is spaces that don't have any strata of odd codimension at all. Because then it's evident that this is an isomorphism. And a very large such class is complex algebraic varieties. complex algebraic varieties are width spaces. Well, if they are pseudo-manifolds. Of course, not every algebraic variety is really a pseudo-manifold, but if it's a pseudo-manifold, then certainly, as we have discussed, using Whitney's process, they are Whitney stratified. But due to the singular, this is what I explained in my first lecture. If you stratify it, you will only get strata of even codimension, right? Because they are all algebraic. They again, the singular sets, they are again all algebraic, given by algebraic equations, and therefore they will all have even dimension. So this is a huge class of width spaces. So therefore, everything I say here is applicable to complex algebraic varieties in particular, right? That's an important class. So suppose X is width. And compact and oriented. In that case, we can now define a signature as follows. And the dimension n is divisible by 4. So you see, for such a space, the Verdier dual of ICM, well, according to our general theorem that we proved, is ICN, because these are dual to each other. But because for a width space this is an isomorphism, this is again ICM. Therefore, ICM is dual to itself. That's an example of a self-dual sheaf. This is called a self-dual sheaf, i.e. ICM X is what's called a self-dual sheaf. It's dual to itself. And also, of course, in terms of global invariance, I can now look at the middle dimension, which is 2k with the lower middle perversity. And so what does the intersection form look like that we had over there? Then this is also 2k. Here I would have to put n, but now I can put m because of the self-duality, right? So I can say, so then this is 2k. Here I would have to say n at first, but I can immediately replace it by m because of this. So I get a non-degenerate symmetric form and it's a form on one vector space, so it's a quadratic form. And so we say the signature, so we get a signature. The signature of x, I'll write it as sigma of x, is the signature of this quadratic form. So we see using intersection homology, width spaces have a signature, and therefore also, for example, complex algebraic varieties, even if they are completely singular, they just have to satisfy the assumptions. So it should be, say projective, right? And it should be a pseudo-manifold. All right. And so one would now have to investigate the properties of this invariant and see whether the properties are indeed analogous to properties of the signature for manifolds. Right, so this is our next task. And the chief property that the signature has for manifolds is its Bordism invariance. So this is what one has to verify first, right? This would be rather useless as a construction if it were not a Bordism invariant of singular spaces. But what does that mean, right? So we haven't really talked about Bordisms of singular spaces. Therefore, we must say something about this. So I start with a definition of a pseudomanifold with boundary. A pseudomanifold with boundary is a pair X, and then there is another space, some subspace of X, which I call the boundary, but it's just a word at this point. It's just some subspace, such that three conditions hold. Firstly, the complement is a pseudomanifold so I omit the word stratified. I mean with stratifications, but I don't write it every time. Is a pseudomanifold of dimension n, say, and then this subspace itself, considered in its own right, is a pseudomanifold of dimension n minus 1. And now you have to say something about the relation between them. And what we say is we want a color. Boundary X has a stratified color in X. That is to say, that is there exists an open neighborhood say U of boundary X in X such that there is a homeomorphism that relates U to 0, 1 cross boundary X. And so boundary X comes with its very own stratification because it was assumed in condition 2 to be a pseudomanifold. Therefore, this product comes with an induced stratification. I just multiply the strata here by this interval. This also inherits a stratification from this, and then the homeomorphism is supposed to preserve these strata. So let me give you an example. Here is an instructive example. Take some manifold and suppose you have a codimension 1 submanifold in it. In fact, you might as well literally take this picture. Say you take a circle with 2 points in it, like I've drawn it, right? Now you collapse these 2 points to 1 point, or more generally, you collapse this codimension 1 submanifold to a point. So then you obtain something like this. Right, so you collapse, and then you identify and you have this space. Is this a pseudomanifold with boundary if I take boundary X to be this circle together with this figure 8 here? Does this satisfy the definition or does it not? So the problem is that you have a perfectly nice color on this side, but you don't have one here. There is no collar here. Because you collapse at the very last moment, so you cannot find a neighborhood of this that looks like a product of the figure 8 with an interval, right? So it's not a pseudomanifold with boundary, and you're not supposed to do that, right? One has to be very careful about this, because otherwise you could try to make Bordisms by collapsing all kinds of things, and you would say, well, they're all Borden to each other, and you would get into terrible trouble later. Terrible trouble. So you have to make this very carefully. Of course, you say to me, all right, but I can just repair this by attaching an external collar. Well, if there isn't a collar, I just attach one from the outside, right? What's the problem? Aha, okay, so let's attach one from the outside. So we attach one from the outside, fine. But now you must think about how do I stratify this? You must think now. So there are funny things going on in the interior, and how exactly do I stratify this? So by attaching this from the outside, you've just moved the problem to the interior in a way. That's the cost that you've incurred by doing this. Namely, you must, of course, for this to be satisfied, you must take this as a singular stratum, but then there is this point at the end, and you must stratify this as a separate stratum. And then depending on what you want to do, you will perhaps have to verify that this satisfies some conditions. For example, if you want to verify that this is in fact a width space, you must verify the width condition at that point. So you must think about what is the link now of this point actually with this construction, and does it have vanishing intersection homology and so on. So there is no free lunch by attaching these outside things, right? So that's what one should have in mind, should keep in mind about this definition. And the theorem now is as follows. And this is also due to Goreski and McPherson. Perhaps one could mention Siegel here as well if one views it on width spaces. I think Goreski and McPherson first did this for spaces with only even codimension strata, but it's equally true for width spaces, which is the following. If xn, now of course I call such a pair a width space with boundary in the obvious way, right? I require that this is a width space, but then actually it will follow from the other axioms that this boundary is a width space also, and etc., right? So this, in that sense, I can say if xn, boundary x, is a compact width space with boundary, then, and here I want to assume that n minus 1 is divisible by 4, then the signature of the boundary, which is then also a width space, vanishes. And really, the proof proceeds in much the same way as you prove this for manifolds. So recall, I mean, this is a theorem of Thom's in the case of manifolds, and there, if if the space is the boundary of something else, you look at the cohomology that comes from the interior and look at its image in the cohomology in the middle degree of the boundary, and it gives you what's called a Lagrangian subspace, a subspace of half the dimension on which the intersection form vanishes identically. And that implies that the signature is 0. That's the proof. And you do essentially the same thing here, but instead of ordinary cohomology, you use intersection homology. And that's it, right? That's the proof. So it's not so hard to show. Well, so now we are in business to consider Bordism on a serious basis, because we already know that we have at least one Bordism invariant, which is this signature. So we can define Bordism groups. So you define in dimension I width Bordism groups, omega width in degree I, like this. You say these are represented, and I'll write square brackets for equivalence classes under an equivalence relation that I will, under the relation of Bordism, right, which I'll explain in a second. So here X is a closed I-dimensional width space, always oriented. Width spaces are always oriented. And the relation is that you say X is equivalent to X prime, and you say width-bordant, right? The relation is width-bordism. You say they are width-bordant. By definition, precisely when there exists a compatibly oriented width space with boundary such that the boundary is orientation preserving PL homeomorphic to X union X prime, or maybe negative X prime. I mean, this is the usual thing you say for Bordism. Right, so you just take the same Bordism relation that you have for manifolds, but you just put the word width in front of everything. So this becomes, if you've never seen this before, this becomes a group, an abelian group under disjoint union of two such X. And if you do the same thing with smooth-oriented manifolds, you get a theory omega SO star. And these Bordism groups are very hard to compute, were very hard to compute. They are understood. But if you want to understand this is actually very complicated. So these groups are very complicated. It's very hard to understand the torsion precisely in these groups. But let's see whether we can compute the width Bordism groups. And we will see that actually this is much easier. So in a sense, singularities, the presence of singularities, although generally is thought of making things more difficult, it can also make things much more easy, much easier, as we will see. But let me maybe make an example first. Let's look at CP2. That's a manifold, but every manifold is also a width space, of course. So we have to remember all the manifolds are of course included in the class of width spaces. It's a much bigger class of spaces to which the signature extends as a Bordism invariant. So CP2 has signature 1. And this just uses manifold theory. So you conclude from Thom's theorem that CP2 is not the boundary of a compact 5-dimensional manifold. Now maybe I shouldn't call it W. Let me call it M. But a priori, it could be the boundary of a singular space. For example, it could be the boundary of a width space. I mean, requiring a manifold to bound another manifold, so another smooth object, is very difficult, right? That places a lot of restrictions on the space. It's much easier to make it bound something that has some singularities inside, right? That should be intuitively clear. If I don't require the co-bounding thing to be smooth, things become much simpler. But the theory that we just developed now shows that CP2 is not even the boundary of a width space. And that's a much stronger theorem than saying it's not the boundary of some manifold, right? A much stronger theorem. So I think that's a good example to keep in mind. Intersection homology theory, as explained above, and width space theory shows, however, that CP2 is in fact not even the boundary of a width space, W. And this is a much stronger theorem. So I think that's an interesting example. Now, as for the computation of these width Bordism groups, I have to introduce an object which are called the width group, an algebraic, purely algebraic object called the width groups of Q. And that's in fact, that will explain the name width space. You may have wondered already what width has to do with these kinds of spaces. Clearly, he doesn't directly have anything to do with them. He certainly didn't develop this theory, right? So what does width have to do with this? But Siegel gave the name width spaces due to the relation to width groups, which were investigated by width, of course. So I'll discuss the width group of the rationals. Since I work with rational coefficients, I only need to consider the width group of the rationals. So I consider pairs V, beta such that V is a finite dimensional Q vector space, and beta is a symmetric non-degenerate bilinear form. And I consider an equivalence relation on such pairs And the relation will come in, I'll state it in a second, the relation will come in forming the width group of Q. So this group will be the free abelian group generated by such pairs, V beta, modulo this equivalence relation. And the relation is as follows. Actually, there are two types of relations. One is if I take in the free abelian group the sum, the formal sum of two such pairs, then I want it in this quotient, in the width group, I want it to be the same as if I took the direct sum of the two vector spaces and the orthogonal sum of the two forms. So here this is orthogonal sum. Block matrices, right, in other words. And that's one relation. And the other relation is if there exists what's called, so I've mentioned this before, if there exists a Lagrangian subspace, so again, if there exists a Lagrangian in V, so again this means that the form vanishes identically on L, and the dimension of L is 1/2 of the dimension of V. So this can only happen, of course, if the dimension of V is even. If V has such, and this really comes from Thom's proof of the Bordism invariance of the signature, where he constructs such a Lagrangian coming from the cohomology of the interior. If there exists such a Lagrangian, I want in the width group this element to be 0. So I mod out by all those. Those become trivial in the width group. Okay. And now the theorem of Siegel is, so, well, first of all, I can do the following. If I have, so perhaps one very easy observation first. For odd I, omega I width is 0. Why? Because if I have an odd dimensional width space, I can simply take the cone on it. That now will have even dimension. So the cone point is a stratum of even codimension. So if x was width before, the cone on x is width again, right? And if you take the boundary of the cone again, then you just get x. So we've shown it's null bordant, and therefore the entire group is 0. And this already shows you, in a way, the philosophy that I outlined over here, that singularities can actually help you to make Bordism questions much simpler, because you could never do this for manifolds, right? You cannot simply take the cone on something and then look at the boundary and then and thereby show that something is null bordant, right? This is a huge singularity that we introduced by just taking this cone. But it works for odd dimensions because this is a width space. Whereas, for example, if you look at this group in odd dimensions, it's certainly not always 0. For example, omega 5 SO is isomorphic to Z mod 2 and is not 0. There is a little generator. In fact, Dold has constructed this. There's a famous Dold 5 manifold, and it's in fact an entire family of manifolds that Dold has constructed. And he showed that this is a that this is a generator. It's non-zero here, first of all, by Stiefel-Whitney class calculation, but in fact it's the generator of omega 5. So certainly this is not true in the world of manifolds. But here it is true. But what about the even groups? So here then is what Siegel says. Siegel says that the invariant that you should consider is you should, let's say I is for k. Then to an xi, to a class xi, in omega I width, you should associate the intersection homology group in the middle dimension, 2k, as I say, with rational coefficients. So that's your V. That's your V. And you should take beta to be the intersection form. On this vector space. And this you should regard as an element in the width group. And then you think for a second and you see that this is in fact well defined, right? So if you change this by Bordism, then this element will be the same, but this is a kind of an argument like over here for the signature. So this is in fact a well-defined map. The first thing you check, and then the theorem is, and this is a theorem of Paul Siegel's. So you get a map, right? So let's call this map W. You get a map from width Bordism to this width group. And first of all, well, we have already seen that in odd degrees this is 0, but in degrees divisible by 2k this is also true. So this group is 0 for I positive and I not congruent to 0 mod 4. Of course, in degree 0 is special, and there you just get z. That's not very interesting. But then, in the remaining cases, for I greater 0 and divisible by 4, omega I, this map W that we considered up here is an isomorphism to the width group. And this is where the name comes from. And so this completely computes width Bordism. It's completely understood. It is a substantial theorem to prove this. And of course, Siegel has to work hard using PL cycles. Essentially, the proof is to make singular surgeries. You take cycles that you don't want, and you try to excise them. You try to remove them, essentially by taking a regular neighborhood around them, taking out the interior of the regular neighborhood and coning off the resulting boundary, introducing a new type of singularity, of course, but killing the cycle that you wanted to remove. Now, once you have all cycles from the middle dimension removed, you can cone off the entire thing, because then the width condition will be satisfied at that very last step, because there's nothing left in the middle homology anymore. And that's essentially the proof. Right? So this is, although this is, you have to technically do quite a bit of work in order to achieve this. It is still much simpler than what people had to do to compute this, right? I mean, this is substantially harder than this. Okay. Well, now you might be worried, well, perhaps maybe this is not so well understood, and so this doesn't give me any information. But so maybe I mean, the structure of this, however, is also completely understood, and this is the work of Witt. I mean, this actually is completely understood. It's given by Z, and this actually has the interpretation as being the Witt group of the integers. But anyway, this part of the isomorphism here is given by the signature. So this Z, the signature records part of this information, but there's more information. The signature is not the only invariant that computes this. So then there is actually, contrary to manifolds, you have here an infinitely generated amount, of 2 and 4 torsion. But how you get that is completely understood algebraically from a form. You can extract all these invariants from the form here. You can compute them explicitly, but there are infinitely many invariants here. So that's a difference to manifolds. And now maybe in the remaining 2 minutes, I can say a word about, I mean, I started the lecture by saying you could now, once you have a signature, if you remember the first day, I said, once you have a signature, you can use it to make characteristic classes. So one could now go yet further and try to make L classes, characteristic L classes, using that signature. And this has been done, of course. So, using a method of Tom, one gets characteristic L classes for Witt spaces. In fact, one can construct L classes even for more general classes. Witt spaces are not the most general class of spaces that have a Bordism invariant signature, is now known. But at least for Witt spaces, I mean, I cannot go as far as that, but at least for Witt spaces, there are L classes. Because if you have a cohomology class, you try to represent it by a map to a sphere. And this is possible in a range of degrees. So if n plus 1, the dimension of the space, is less than twice the dimension of the degree of the cohomology class, then a theorem of Serre asserts that a cohomology class is really the same as a map to a sphere. And once you know this, you triangulate the sphere. So everything triangulated, and then by the simplicial approximation theorem, you may assume that this is in fact simplicial. And then you take a point P in the interior of a top-dimensional simplex in the sphere. And you take a pre-image. Let's call this map F, and you take a pre-image of that point. And the main observation is that the PL topology allows you to say the following. The fact that the map is simplicial allows you to say, if you take the entire pre-image of the entire open simplex, this is of course not true for the closed simplex. It's very important that you consider the open simplex. But if you take the pre-image of the open simplex, then this looks like F inverse P cross delta K. And this follows because the map is simplicial. So it's linear on every simplex, so it's an easy exercise to show this. Now once you know this is what I called earlier, or perhaps in the problem session we talked about this briefly, a normally non-singular inclusion. Because this of course looks like RK, so you know that this is a space that has a neighborhood in the singular space, which however looks like a product with RK. That's rather special, but it happens because of that pullback. But this will in turn mean that if X is width, then the pre-image is again a pseudo-manifold, width, everything you want. So you have a signature defined for that pre-image. So you get a number. So this gives you a map. Doing this kind of process gives you a map from here to Q if you regard the signature as a rational number. But by the universal coefficient theorem, a map from the rational cohomology to Q is the same thing as a homology class with rational coefficients. And you define this, right? So you have this element in here, and you define this to be the L class. And so this is a very brief overview of Tom's method as applied by Goreski and McPherson to obtain an L class even for singular spaces, even for width spaces. If you apply this process for X a manifold, then what you get here are the Poincaré duals of the Hirzebruch L classes defined via the tangent bundle. So time does not permit me to speak more about the properties of this L class now, so I think I'll just leave it with that. Thank you. Are there any questions? Yeah.
One often sees these L classes as being like terms, polynomials in the Pontryagin class, or in the curvature, let's say, in differential geometry. Is there any approach of these classes as being like piecewise, and at each stratum having some curvature and like glue that together?
Not that I know of. Not that I know of.
So like a Chern-Weil theory for...
No, no, not that I'm aware of. No. That doesn't exist, at least at present. Yeah, yeah. I don't know whether that can in fact exist. I mean, of course, there is Cheeger's work, perhaps one should mention, on the L class. So Cheeger, of course, has very beautiful formulas for the L class in terms of eta invariance. So it's of course an interesting question. This is a homology class, so it's of course represented by some cycle here. So can one give an explicit description of a cycle, right, as a formal sum of simplices with certain coefficients that represents that class? And this is a long-standing problem, in fact, in general, even for manifolds, for the Pontryagin classes and so on, to find an explicit combinatorial description of the Pontryagin class in that sense. And now Cheeger has a formula in that spirit, although it's not combinatorial. It sort of involves the eta invariance. And so Cheeger says if you want to compute the L class, you can write it as a sum over all the simplices of dimension k times the eta invariant of the link of that simplex. So that is one thing you can say. Are there other questions? Okay, doesn't seem to be the case. Thank you.